Okay, back for video 4. Made a couple changes. I made my results 14-point font. I spread out the matrix for the DC circuit. I spread out the coefficient matrix for the AC circuit, make it a little easier to see. These were our results. I got to get to Scilab. There's Scilab. I also, up here I measured 1,4, the current through the capacitor times the capacitive reactance. This is the voltage I got, and then because they're in parallel, had I chosen the other current, the current through the resistor times the resistance, this was the voltage I would get. And as you can see, they are the same number. So I want to now go back into LT Spice and I want to build the circuit. And the first thing we're going to do is get rid of our 3K in favor of a capacitance. And I've got to rotate it and put it in place. I'm going to have to extend the line. So very simply, I got the capacitor in there and now the inductor. And you don't have to turn off scissors, you just have to select something else. So there's my inductor. Okay, just like I did the values last time, I'm going to hover over the part, right mouse click, and then type in the value. And Spice does recognize the lowercase u as micro. And then for my inductor, I'm going to hover over the part, type in the value, and there is no metric prefix there, so that one's good. The only other difference between this schematic and the one on the handout is that this is now an AC source. So I'm going to erase my DC value and click on the Advanced tab. We'll change it up here. This is one thing where this can be a little confusing. I'm going to do a small signal analysis to start with, and then we'll look at it in terms of what it would look like on an oscilloscope. Spice is calling for amplitude. If you put in amplitude, it will give you amplitude. Typically, though, in industry, in circuits, you're dealing with RMS. So if you pretend that your amplitude is really your RMS value, then the answers it gives you will be RMS values and not amplitude values. So I'm changing my small signal to 24 volts AC, and then I can click OK, and then I've got AC 24 down here. I have to change my analysis a little bit, so I got to go in and edit my simulation command. We were doing DC analysis, and if you do DC analysis with a capacitor, the capacitor's an open circuit and the inductor's a short circuit, so it'd be like they would not even be in the circuit. You'd only see a voltage drop across the resistor. We're going to do AC analysis this time, and this is for sweeping through many different frequencies. So again, I choose linear. Normally I choose 1 point and I choose the frequency I want my analysis at, and so that is my start frequency and my stop frequency. If I want to sweep through multiple frequencies, I could do it either as a doubling, or I could do it as a times 10. I could put in a linear list, a linear frequency sweep, or I could just list it. So I want a linear. Okay. Stop, start, frequency. It's building my simulation command down here in the corner, which you could just type in. And again, once I finish the analysis, it's prompting me to click it somewhere in my schematic. So when I click that, what you notice is that my dot op over here became a semicolon, which means that SPICE has commented out the DC analysis in favor of doing AC analysis. Now if I do a simulate and a run, I get my voltages and my currents. Now interestingly, my voltage from 1 to 0 is 24 volts. My voltage from 2 to 0 is 28 volts. So if I do the subtraction, I get 28.14 minus 24 gives me about 4.15 when I did SPICE analysis. So if I come back over here to the spreadsheet, I get about 4.15 in SPICE. 4.15 volts in SPICE. And then I get the 28.15 here, which is effectively the same as what we calculated by hand. Same as last time. Something to point out on the currents. I still get my currents. So had I gone in and did the magnitude, if you will, or the absolute value of the currents that I did in Scilab, I would have got these numbers for IC, IL, and I8 or IR. And these are actually the phase shifted, or the angles that they would have had, those currents would have had. So in the AC circuit, you talk about a magnitude and you talk about an angle. That's important to remember that your meter, if you're measuring or analyzing a circuit with a meter, it's not going to show you the phase angle. It's only going to show you the magnitude. So that's sort of the values you want. Okay, so I can get perfectly adequate results with this. If I'm looking for just currents that I'd read with a meter, voltages I'd read with a meter, I've got it. Okay. Need to go back to Scilab for a minute because I want to do a quick calculation. I need to know the period of a 60 hertz sine wave. And the period is 1 divided by 60, or 16.7 milliseconds. I'm going to say 17 milliseconds. And I'm doing this for my next analysis. Period 17 milli. So 1/10 of that would be 1.7. And if I wanted to see 3 complete sine wave cycles, that would be 17 times 3, or about 51 milliseconds. And you'll see where those numbers go in just 1 second. Okay, so what would it look like on the oscilloscope? Okay, that's a little bit different analysis. I have to go in and edit simulation command again. And this time I'm going to go to what we call transient. And my transient analysis requires that I do a stop time, a time to start saving data, and a maximum time per step. Basically, our maximum time per step is we want to sample 10 times in a cycle. So that would be that 1.7 milli. If we want to see one cycle, we could start at 0 and we could end at 17. Sometimes when you're starting up a circuit, however, you'll see a true transient, and we want to see more of the steady state after everything gets gets where it wants to be. So sometimes we delay our start time 1 or 2 cycles. So what if I delay by 34 milli, and then I add 51 to it, so I do 85 milli. Okay, this should show me a sine wave, or what it's behaving as. The true transients that you would study, say, in an engineering school, doing DC and AC analysis. What happens when this capacitor first charges? What happens when this inductor first charges? That's what I can truly consider the transient. And then later on, after everything started up, things come to a steady state. That's no longer a transient anymore. So I'm using transient analysis, but I want to look at more of the steady state waveforms that a student would see on an oscilloscope in a lab. So I'm building my steady state transient waveform, and now I've got another simulation command, and you see that transient is now the one that is going to do, and AC and op are gone, and you can cut them out if you want to. The other thing I have to do is go over here to my voltage source. When you do small signal AC analysis, you put in your amplitude here. If you want to actually see it in a as you would see on a oscope, then you have to build your signal over here. You can do sine wave, obviously, is a sine wave, and pulse gives you time delay, time rise, times fall. So you can build your square and your triangle waves in here if you are if you think about it, because you know what your time is for rising and falling. You know what your period is. You know how many cycles you want to see. Okay, for just a plain sine wave, you just click on it. It knows it. I don't want any offset. My amplitude, well, if I'm going to look at it on the oscilloscope, I do need to know the amplitude. And the amplitude is 24 divided by 0.7. Because it's got to get bigger, right? 24 divided by 0.7. It's actually square root of 2 over 2. So 33, I'm going to say 34 volts. So I need an amplitude of 34 volts because that's what they would see on the oscilloscope. So 34. Frequency, I actually do put in the frequency here. I can delay the frequency and some other things, but again, we're keeping things fairly simple. And how many cycles do I want to see? Well, my analysis, I'm actually looking through 5 cycles, so let's let it do at least 5. We'll say 6. We're only going to see 3 of them, but we'll have it do more than what we want to see. Otherwise, your waveform can just stop on you. So click OK, and I got things on top of each other here, so let's move that down a little bit. So it changed my sine wave, and these are all the parameters that it's feeding it. Again, as you learn this program, you can type it in manually. And one of the things I haven't shown you is view. If you happen to have a visually impaired student, this is this circuit as a text file. So V is voltage, R is resistance, C is capacitance, L is inductance. I've only got one inductor, one capacitor. I could change that, like I changed the R8 to 8K. I only have one voltage source. And so basically you can put in all these parameters as a text file, and then you can put in your analysis. And anything with a semicolon is commented out, and then you can simulate it. So this is the primary reason I picked SPICE. I did have a visually impaired student, and all this is graphical, what we've built so far, but you could actually type it in. And this gets back to the native SPICE that was developed. It used to be very text oriented, and you had to put in stuff right. So you have the voltage, you have the numbers, then you have your nodes that the source is between, or the load is between, and then the value of them. So pretty straightforward, simple. And so that was the only way I could get that student to analyze circuit, and that put her on the same level as the others. Now, she didn't visually see the results. She had to have them read to her off the screen, and that was not the best, but it worked okay. And this is why this is another reason, other than cost at Multisim, and there's some other softwares, but if you can't do the net list, then I don't know, it's just not as good in my mind. Alright, I'm off topic again, so let's run it. And what opens up is a screen that looks like an oscilloscope. So you have a time base here, and you're basically going 0 to 51. And this is from where you're starting to where you're ending, which is actually 30 seconds or so into the simulation. So if I click down here and hit the space bar, the space bar is your friend, I can look at the voltage level at different wires. All I have to do is click on the probe. It's going to show me the voltage level at point number 1. And we basically put in a 34 volt peak to peak signal, and there's your effectively 3 waveforms that we were shooting for. And if I want to look at the voltage on point 2 with respect to ground, all these are with respect to the 0, I click there. Now what you see is I have a capacitive voltage. So everything's shifted, my scale has changed, and I'm actually getting a higher peak on my capacitor, peak and valley. And it's actually changing in time. So this is what a student would see on an oscilloscope. If you want to see the current through something, it will actually graph it. The current scale will show up at this end. You'll get another graph. Usually I stick to doing voltages because that's the only thing you can effectively see on an oscilloscope. But you can actually see if you had a phase shifted waveform. And there's a little bit of a phase shift here, it looks like. Yeah, maybe not. So this is what it would look like on an oscilloscope. And there are, of course, better circuits where you can really see a phase shift across the components, and you can see that one voltage peak and another voltage peak happen at different times, and you can visually see the phase shift. And that's what I wanted to show you in the in LT Spice as far as transient analysis. So there's the simple DC analysis, then there's a AC analysis if you just want numbers, and then if you want to see what it's looking like on an oscilloscope, there's transient, and there's a few things you got to do to make AC and transient work, but they're not insurmountable. And then you've got your solution. Okay. So 51 milliseconds, and I think our amplitude had to be 34, right? So that's technically a V peak, and we needed that number as well. And so those are my results. Okay, all that to show you what happens in DC, AC, and then you can troubleshoot. I mean, I can go in and you can open and short, and everything changes. Just like we did with the DC circuit. You can open and short stuff and predict what will happen. And then students can sort of get a feel for it. And you can get a lot of experience doing the troubleshooting aspect, because this gets us back where we want to be, and that is, what does industry want? And so here you go. Page 3. What does industry want? Industry would love to have somebody that could come in and troubleshoot this circuit if it fails. And this is a pretty common circuit in industry. And what I've done is I have actually left the as is with no fault conditions in there for you to fill in the voltage table. And then I've given you some fault conditions. So if I read, and this is reading 3575, which is this wire number to a common, which my common's over here on this side of the motor and the safety relay. I've got all my voltages. What would they all read as I come across? And that's with the circuit as you see it, with nobody pushing a button. And then I've got some fault conditions where I say, okay, these are the voltage values you get with my start button pressed. What is likely to be my fault? And that's what industry's looking for. They're looking for somebody who can interpret a circuit and figure out what's wrong and fix it. Not just guess and change parts, but actually figure out what the single fault is, verify that that fault is actually the fault, and then replace the part and the machine's running again. Okay, probably the biggest thing in industry that people don't realize is if I make these measurements here across my top row as is, I'm assuming the circuit's on, and I'm assuming everything's in the condition it's shown. So in that case, you would assume that this heater is closed, this safety relay is energized, and so this set of contacts is closed. In which case, what I will get is I will get 24 here, I will get 24 here, and then I will get 0 from 90 to 95 and 3600. So I'll get a 24 here, a 24 here, 0, 0, 0. What I will get here is I will get 24, because 24 here, 24 here, so my 24 volt drop will actually be across the safety relay. In this particular rung of the ladder, my 24 volt drop will be across the open. That would be my normal conditions. And it takes a little while, it takes a little skill. And one of the things about DC circuits is you can have a string of resistors in there, and you can go in and open and short them, and somebody can measure them, and then they can sort of get to where they can see this stuff and say, hey, I've got 24 volts where I should have a 0, which would be the case here, and then I need to go look at my over travel limit switch. It's either open and I'm not expecting it to be, or it's broken. So anyway, that's what industry wants. They want troubleshooters, people that can efficiently and effectively troubleshoot. And I left more things so you can go in and think up a possible bug if you're the instructor, and with certain conditions, and then based on the bugs you put in, somebody's got to interpret and say what's most likely the fault. So if I fill this in, my normal condition, I get 24 here, 24V, 24V, and then I'm a 0, V, 0V, 0V, and 3650 is 24V. And that's my normal. Now what happens if I get 24 on 3490, but I don't have it on 3595? So I've got 24 volts here to here, and I got 0 volts from here to here, which means I have a 24 volt drop across my over travel limit switch. So my over travel limit switch is either open or it's broken. There's something not right about it, because my circuit's not working. Because usually if my start is pressed and my machine's not over traveled, it should start. assuming it hasn't overheated. So that's what I'm expecting. And so then I've got different fault levels in here that you can troubleshoot, and you can basically go in and you can open and short everything. I could short this set of contacts. I can open this. I can open the stop button, which I think is one of these. I can open the heater and just figure out why the circuit doesn't work. And yes, you can do a lot of troubleshooting on the board. You can do a lot of troubleshooting in theory, and it's a little different. You got to learn how to actually measure and get to these things. But this is where we start in DC with a circuit like this. You can troubleshoot. You can build this all day. You can open and troubleshoot, and then somebody can get the confidence that they can measure and find the problem right the first time. Anyway, I appreciate your attention and everything, and I hope this helps. And this concludes the video series on A Taste for Industry.